Today we're going to talk about eigenvectors and eigenvalues with Deandra James, Morgan Lampley, and Terry Thomas. So what exactly are eigenvectors and eigenvalues? An eigenvector is a non-zero vector x such that ax equals kx, and an eigenvalue is a scalar k such that ax equals kx has a non-trivial solution. So how do you find these eigenvalues? Well, we know that ax is equal to kx. So from here, we subtract k times the identity matrix I times x from both sides of the above equation. On the right side of the equation, the identity matrix times any vector will give you just the vector, so it's 0 on the right. And on the left, you have ax minus k times the identity matrix times x. Factoring this on the left side gives you a minus k times I times x equal to 0. We also know that for k to be an eigenvalue, the equation ax equals kx must have non-trivial solutions. Since this equation is equivalent to a minus k times I times x equals 0, this means that the matrix a minus k times I must be what we call singular or non-invertible. Since the determinant of singular matrices are always 0, the determinant of a minus k times I must also be equal to 0. Setting this equal to 0 produces an equation in K, what we call the characteristic equation. Solving this equation will produce the values for K and thus give you your eigenvalues for that matrix A. If the matrix A is triangular already, then its eigenvalues are the entries along its main diagonal. So how do you find eigenvectors? To find the eigenvectors corresponding to each eigenvalue, you must substitute the eigenvalue back into the original equation and solve for x. To find all the eigenvectors of A, this must be done for each and every eigenvalue that you find. And here's an example. So say we're given a matrix A, as shown here. You must take this matrix A and subtract k times the identity matrix I from it. And you'll get a resulting matrix such as 2 minus k, 3, 3, and minus 6 minus k. The determinant of this matrix, which is a 2 by 2 matrix, should yield the following: 2 minus k times negative 6 minus k minus 3 times 3. And this result will give you the characteristic polynomial. Since the determinant is supposed to be equal to 0, you also set the characteristic polynomial equal to 0, thus giving you the characteristic equation. Solving this equation will yield you k equals 3 and negative 7. Recall that a minus k times I is the following equation. You must substitute your first eigenvalue, which is 3, back into this equation, and it'll give you the following matrix. Then you set that equal to 0 and augment the system, and it will give you the following. And solving this equation, or this matrix, you will see that x1 is equal to 3 times x2. Thus, your eigenvector for the corresponding eigenvalue 3 is 3, 1. And you repeat that for your other eigenvalues and each thereafter. So how does this apply to the real world? It applies to the real world in examples such as population growth. So say that a population of rabbits has the following characteristics. Half of the rabbits survive their first year, and of those, half survive to their second year. The maximum lifespan for these rabbits is 3 years. During the first year, there is no offspring. The second year, there's an average of 6 offspring, and the third year, an average of 8. So given that x is the age distribution vector of the population from one year to the next, it is related by the following equation. In this equation, A is called the age transition matrix. So from here, you find an x such that the percentage of rabbits in each age group stays constant each year. This means find an x such that for each specific year, x is always some constant k times the age distribution vector of the previous year. That is, x such that x equals to a times x, which is equal to k times x. You find the matrix A by doing the following. The first row is the offspring produced in each year. The second row is the probability of surviving the first to the second year. And the third row is the probability of surviving the second to the third year. Each column consists of each age group. Therefore, you would get the following matrix A with our scenario. And then you move on to solve for A minus K times I, as we've done before. Find the determinant by cofactoring. And solving for the determinant of A is equal to 0. From here, you are now able to find your eigenvalues, which in this case are 2 and -1. If you substitute each k into the original equation, it'll result in the following augmented system. We choose the positive value as an example, which is 2, and you go back and repeat all the steps as shown before, and it'll give you the following eigenvector: 16, 4, and 1. That means that the eigenvectors of this form, where c is a scalar, will always have the same percentage of rabbits every year.